Welcome and thank you for joining this webinar, From Processor-Centric to Data-Centric Computing, Architecting the Future of Intelligent Computing, prepared by the Alpert Research Team. We adopted the von Neumann model because its unified memory made writing software universally easy. We built entire ecosystems of compilers and operating systems around this beautiful, flexible abstraction where data and instructions just live together in harmony. But if I'm understanding this right, the very foundation of our software success is what is currently killing our hardware performance.
The ultimate flexibility of von Neumann means that every single thing a computer does, every instruction fetched, every piece of data read, every result written, must squeeze through that single shared bus. And this brings us to the exact physical limitation that is currently holding back the entire tech industry: the von Neumann bottleneck.
How do we actually calculate the bottleneck?
The effective speed of your entire computer system is limited by the minimum of two variables: either the maximum rate your processor can execute operations or the maximum bandwidth of your memory bus.
So you can engineer a processor capable of performing 1 trillion calculations per second.
But if your copper memory bus can only physically deliver enough data to sustain 1 billion calculations per second, your processor speed is completely irrelevant. It will perform 1 billion calculations and then spend 999 billion clock cycles just sitting idle, waiting for the bus to deliver the next batch of numbers.
But earlier you said this isn't just about speed, it's fundamentally about energy waste.
And to understand why, we have to look at Landauer's principle. In physics, Landauer's principle states that there is a strict theoretical minimum amount of energy required to change a bit of information, like to erase a 1 or a 0. It's a fundamental thermodynamic limit.
In our practical classical silicon systems, we aren't anywhere close to that limit, are we?
No, we are operating millions of times above that theoretical limit. We are incredibly inefficient. The vast majority of that wasted energy isn't going into the logic gates doing the math. It's going into the wire.
Because of the equation for wire energy, E equals CV squared.
Energy, the E, equals the capacitance of the wire, the C, multiplied by the voltage squared. Capacitance is essentially a measure of how much electrical charge a physical wire can store.
And that scales directly with the physical length of the wire. A longer wire has higher capacitance, so it takes exponentially more electrical energy to push a signal down that wire.
And the distances in a computer are microscopic to us, but relative to a transistor, they are massive. Moving a piece of data a few micrometers across a processor chip might cost a few picojoules of energy, but moving that same piece of data completely off the chip, across the macroscopic copper traces of the printed circuit board and into the DRAM memory module, that can cost hundreds or thousands of picojoules.
In a typical AI workload, the actual mathematical computation, the part we actually care about, is consuming maybe 10% of the energy budget. The other 90% is just pushing the numbers through the capacitance of the copper wires.
And this creates a catastrophic roadblock for the future. We are currently trying to scale up to trillion-parameter foundation models, but as we pack more transistors onto chips to do this math, we run into the dark silicon problem. Thanks to Moore's law, we have been able to shrink transistors so small that we can fit tens of billions of them onto a piece of silicon the size of a postage stamp. But we haven't been able to shrink the operating voltage at the exact same rate. This means the power density, the amount of heat generated per square millimeter, has skyrocketed. If you actually tried to supply power to all 50 billion transistors on a modern chip at the exact same time, the cooling system would fail instantly. So you have to leave huge sections of the chip powered off at any given moment. They remain dark.
So you can only light up a small percentage of the chip at once.
The von Neumann architecture will remain foundational, but AI-scale workloads are exposing fundamental limits in memory movement, energy efficiency, and scalability. Future systems will increasingly combine heterogeneous accelerators, memory-centric computing, and post-von Neumann paradigms to create intelligent, distributed compute fabrics spanning the edge-to-cloud continuum. Organizations that fail to adapt risk falling behind in the next era of AI-driven computing. If you are interested in gaining a deeper understanding of the transformative power of wireless technology, join the Alpert Research Team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.
Thank you so much for joining us on this deep dive into the physical and architectural future of our industry. Keep exploring, keep questioning the paradigms, and we will catch you on the next one.